All right, so we talked yesterday about using vectors to do proofs of geometric statements, and we talked about how you could think about parameterizing a line. Actually, I didn't use those words. We said you could think about a line as being given by going to a certain point on the line and then moving in a certain direction, a certain amount. And so we had this sort of general formula that if you had a particular point on the line, you could go there and then add scalar multiples of a vector, which I'm going to call the direction vector of the line. So as t varies, you're moving along the line. T going negative, you go backwards. T going positive, you go forwards. And so we did use this yesterday to talk about where those 2/3 came from when we were talking about the intersection of medians. So we'll come back to this, and we'll use it rather a lot, particularly next semester, but we'll come back to it soon. All right, so far we've talked about what with vectors?
Adding, subtracting.
Adding, subtracting, scaling, length. Anything else?
Moving it around.
Not much else.
Definition of being parallel.
Parallel, but okay. So what other notions do you associate with geometric considerations? Besides lengths of things, areas, angles. So that's sort of what I want to do next. So what does the word perpendicular mean to you?
90-degree angle?
90-degree angle. Everyone agree? Of course, we're supposed to be sophisticated people.
And use radians.
We're not supposed to use degrees. Although one of the Weber problems will ask you for something in degrees just so that you have intuition to check on it, because we don't all think naturally in terms of radians. But so if I draw you two lines, what ways do you have of deciding whether they're perpendicular or not?
Check the slope.
Yes. And what's supposed to be true about slopes?
Negative.
Negative reciprocal.
Negative reciprocals. So perpendicular lines have slopes that are negative reciprocals of one another. You know what my next question is going to be?
How do you know that?
Yeah, that's my question. So you've all memorized this.
You can use the distance formula.
Interesting. What do you want me to do, Dan?
Well, if you check, if you were to draw like a triangle that has the rise and the run,
Okay, where am I supposed to draw
just
this like a triangle?
at the point of intersection to any random point on any of the other two lines. So
Something like that?
no, start at
Just one line to the x-axis.
just and then
Oh, okay, so you're doing what I wanted to do. You're doing it like a
Yeah.
right triangle associated to each of the...
yeah.
Okay, I don't see where distance formula is going to come from.
Well, it's because the shortest distance between a line and a point on another line will be at a perpendicular point. Will be at a perpendicular.
Okay, we'll come back to
Direction.
that actually on Friday probably, but I like this idea of looking at this triangle. If this angle here is really 90 degrees, if it's really a right angle, then that means I should be able to take that triangle
And move it.
and
rotate 90 degrees.
flip it over.
Yeah.
My chalk is completely disintegrating. And move it over so that it congruent copy of it is sitting there. So let's figure out why that's true. So if this vector here is x, and this vector, which needn't actually be identical, so I might actually make it longer just so that that isn't so clear. Make this. So let's think about the x vector there, y vector here, and let's make a blue triangle for y. What can we say about these triangles? Because this angle is a right angle,
Yeah, there's, alright.
the two right triangles are similar. So can we check that?
Yeah.
Yeah.
So let's see. If this angle here is alpha, what is this angle going to be?
90 minus alpha.
Everybody agree? Because you got a pi over 2 here, they all add up to pi, so this is going to be pi over 2 minus alpha, which means, what's this angle?
Alpha.
That's also alpha. So you have two right triangles whose angles all match up. Right? You have a right angle here, right angle here. So the triangles are similar. So what does that tell me? So we'll go back to our notation from yesterday or the day before. Let's say x1 and x2 are the first and second components of x. And let's say y1 and y2 are the components of y.
Then you know that similar corresponding sides on similar triangles have ratios that are the same.
So
x2 over x1 is y1 over y2.
So x2 over x1, which is the slope, isn't it, that you were referring to. Now, be careful, it's equal to what?
Negative
The absolute value of what?
Wait, where'd that negative come from?
I don't know.
The absolute value.
Y2 over y.
So slope is x2 over x1, but on this one we're going to take corresponding sides, so we have to do opposite alpha is this side. But what?
Negative y1.
It's negative y1 because clearly y1 is a negative number here, and so to get that length I
Be a
need to
positive
take
number.
the negative. And then over y2. So this is the fact that you guys were remembering, right? Because this is the slope of the x vector line, and this is the reciprocal with a minus sign of the slope of the y vector line. Agreed? But notice that I can get from this, by clearing denominators of my fraction, x1 times y1 plus x2 times y2 is what?
0.
Right? x2, y2 equals the negative of x1, y1. So their sum is 0. And so that little bit of algebra now looks very tantalizing.
Yeah.
So this leads me to say, let's consider some algebraic construction based on two vectors, x and y, where I can write down this combination of their coordinates. So for two vectors, x and y, in the plane, consider this formula. x1 times y1 plus x2 times y2. And because it's going to turn out that that's something we want to study for the rest of the hour, I want to have some notation for that. So I'm actually going to make up a notation, never heard of before, called the dot product of x and y. And in fact, I'm going to go whole hog here and say, indeed, for vectors in Rn, for any n, let's just do the analogous thing. Let's set the dot product to be the sum of the products of the corresponding coefficients of x and y. And I'm going to make the statement that you can argue with me if you want. This must be an interesting thing to study because of the fact that perpendicular vectors have this dot product being 0. So that already makes it intrinsically something interesting. Right? It's characterizing something geometric, namely right angle, by saying this algebraic quantity is 0 means this is an interesting algebraic quantity. But we want to figure out how much more interesting it really is. So I'm going to sort of do most of my pictures at this point in 2 dimensions, but you can do this computation in general. Okay, so what properties does this thing have, aside from this geometry that motivated it? So, we've been doing algebra versus geometry all week. We'll come back to more geometry. I started with geometry here with the perpendicular lines. Got to an algebraic definition. Let's do some algebra with it and then come back to more geometry. So looking at this formula and thinking about all the algebraic things you've thought about in your lives, what properties might you observe? Well,
Commutative.
yeah. How does it change if you switch x and y?
It doesn't.
Doesn't. Because through the property of multiplication of real numbers, right? x1 times y1 is the same as y1 times x1. So, okay. So this is the commutative property. What other properties do you notice?
Distributive.
Again?
Distributive.
Distributive. Okay. If I take x and I dot it with a sum of 2 vectors, you're saying it should distribute.
Yeah.
Distributive property. Okay, why is that true?
If you pulled all the x's out of your expression up there, you would have y1 plus y2 plus yn.
Whoa, 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 you can't do that.
Oh, sorry, never mind.
Yeah, you can't do that. But if you just start off and you think about what you have to do here, you have to take the first coordinate of x times the first coordinate of y plus z,
Right.
which is,
Y.
right, we defined addition by saying you just add them component by component.
Right.
So the first component of y plus z is the sum of the first components. And similarly, the second one is the sum of the second components. And I won't do all n, we'll just do it for 2. But now you see it, right? What can you do with this? You can distribute by the distributive property with real numbers. So to be super pedantic, and I won't ever be this pedantic again, well, maybe not, never. Right, so you distribute, and now what do I do with this?
You can smooth the z's over here.
Matthew, put that away. I can put the y terms together, and I can put the z terms together. So officially, this is using commutative and associative properties of addition of real numbers. And this is x dot y plus x dot z. Okay. Okay. What other properties?
If you have a scalar for one of,
Yeah, you got scalars flying around. So if you took a scalar times x and you dotted it with y, what would you have? Same as?
Well, x times c.
You just pull the scalar out, right?
Yeah, sure.
These are both going to be extremely important in a couple of sections when we get to defining linear transformations, so these are both very important. Okay, so scalars pull in and out of dot products, and because of the commutative property, the same property would be pulled in if I put it on the y term, right? Okay, I'm not even going to bother to write this one out. You take the definition, and you put in cx's, and you can, again, by the distributive property, factor the c out. Okay. One last one, which relates this to what we did on Monday. What happens if you put in x for y?
You get the magnitude squared.
It's the magnitude.
This is the sum of the squares of the components of x. So that's going to be the length of x squared, or the magnitude of x squared. All right, well, those are the algebraic properties, and what I'm going to claim now is that using these, we can actually get more geometry. So first of all, let's go back and revisit what motivated this. Suppose I had a picture like this. Suppose I had x, and I had y. Then as we did the other day, you would have the sum of x and y. How are the lengths of these three vectors related? So if I asked you to figure out what the length of the sum of the vectors was, what would you do?
Magnitude of x squared plus 2.
Yeah, what? Okay, so you're skipping to the answer. So how are you getting that?
You're treating that just like x plus y and then squaring it.
You make it into a big.
If I want the length squared of a vector, what can I do?
Take the dot product.
Divide it with itself. And then what can I do? Distribute, although you guys were taught somewhere in middle school to call that
Foiling.
foiling. Not to foil your fun or anything. So if you distribute out, you get 4 terms, right? X dot x, which is, I'm tired of this. Magnitude of x squared plus x dot y plus
Y dot x
plus
magnitude of y squared.
y dot y, which is magnitude y squared. And I am going to be pretty mean to you guys. I do not write vector squared on your paper. So if you start writing vector with a squared without putting magnitudes around it, or a dot product, don't be surprised if you lose some points. That's because I'm mean. All right, so what can we do with these two terms?
They're the same.
They're the same to commute commutativity. So I get magnitude x squared plus twice x dot y plus magnitude y squared. Which is a generalization of the usual binomial expansion, but we've got magnitudes and dot products. So what do you notice? When is it the case that the length of the sum squared is actually the sum of the squares of the lengths?
With the perpendicular.
Yeah.
So if the dot product is 0, it starts to look a lot like what theorem? Pythagorean theorem. So we actually have if and only if here, right? You have equality of this with magnitude x squared plus magnitude y squared if and only if this term is 0. And for those of you taking abstract algebra, you can not worry about the fact that 2 times something is 0 may or may not mean that the something is 0. But in all our world, right, you know, twice a number is 0, the number is 0, and vice versa. Okay, so magnitude of x plus y squared is the sum of the squares if and only if the vectors are orthogonal. So we said perpendicular, and I'm actually going to give you a definition of a term here. We say x and y are orthogonal. So that's a fancy word for perpendicular, but you'll see this used all over math and physics. So, anybody know any Greek? Yeah, like orthodox, orthodontist, and gone, like polygon, right? Sides. So you're having straight sides is the origin of the word. And so the conclusion now from this is you have the Pythagorean theorem if and only if you have a right angle. Okay. So I'm still not seeing what this dot product means geometrically other than when it's 0. When it's 0, I see that the vectors are perpendicular. But suppose it's not 0. What does that tell me?
That they're not perpendicular?
Okay.
How much of one
Maybe
vector
it'll
is in
find
the
the
angle?
angle.
Not to be outdone as being a smart ass in the class, yeah. No, perfectly fine comment then.
That's my job. Just talk to Azov.
So let me be more precise. Is there some way you could actually measure an angle using the dot product?
Yes.
Yeah.
So you all have some formula that you know, but where did it come from?
If you look at the 2x dot y term in your formula there, as x dot y gets smaller and smaller, they get closer and closer to being perpendicular.
I agree. But suppose I want to actually ask the question, given 2 vectors, can I use the dot product to actually tell exactly what the angle is?
Yeah.
Yes. So here's how we're going to do that. So all you people who know a formula in physics, actually where I'm headed today in physics, is they use that as the definition. So the geometry is used as the definition in physics courses, and then they make some hand-waving gestures and say, here's a formula that you can actually use. But they don't ever connect them. I'm going to go backwards. So from starting with the algebraic formula, I'm now going to get you that geometric notion. And here's the key idea. We understand angles better if we have right triangles. Because then we have, no, then we have SOHCAHTOA. Right? If you have a right triangle, you know how to get trig functions of angles in the right triangle. There's ratios of sides. So here's my picture I want to do. I want to take my x, and I want to take my y, and I want to think of making a right triangle. So think of these as vectors in the plane. Don't worry for the moment that they might be living in 27-dimensional space. I want to think of making a right triangle by dropping a perpendicular. So this is relating to some stuff one of you was saying earlier, I've forgotten who, about distance from a point to a line. I want to think about, given x and y, and let's assume y isn't 0, or else I'm going to get in trouble with what I'm doing here. I want to think about making a right triangle by splitting x into two vector pieces. One piece that's a multiple of y, and one piece that's perpendicular to y. So this is going to be my perpendicular piece, and this is going to be my piece that's parallel to y. So I want to write x as a sum of a parallel piece and a perpendicular piece, where x parallel is some scalar multiple of y, and x perp is orthogonal to y. And for those of you who are getting tired of all these letters, I am going to do a numerical example in a few minutes. Okay, this is my strategy. Given two vectors, y not 0, think about drawing a line through y, drop a perpendicular, make a right triangle, and I want to now show you algebraically that I can do this and get this picture. Okay, so I mean, again, you're looking at the picture saying, well, of course I can do it, but I want to actually do it just based on the algebraic properties we have, so we'll have formulas for how to do it. So, how can I possibly start with a formula like this and say, how can I solve for what those two pieces are?
Since it's just a sum of them.
No, but I'm trying to use this equation and the properties, which I haven't quite erased yet.
So you can have x dot y and then distribute the dots to each of the components of that.
You're telling me to take my equation and dot it with y.
Yeah. And you already know that the perpendicular part dot y is 0, so all you have to worry about is the parallel part.
Okay? Now what?
Well, because you already defined the parallel part as c times y, a scalar times y, then all you have to do is figure out what c was. And so if you do cy dot y, then you get c times the magnitude of y squared.
And very conveniently, I assume that
Y is not 0.
y isn't 0,
Which is great.
which means this isn't 0, so I can do what with it?
Solve.
Divide. So c is going to be x dot y over magnitude y squared. So we have now shown that if you're going to split x into a piece parallel to y and a piece perpendicular, the piece that's parallel to y is given by this scalar multiple of y. Right? X parallel is this scalar times y. Now, what is x perpendicular going to be?
X minus all that.
And what should you, in principle, stop to check?
That it's, that the dot product is 0.
Good. So the check you should do, but I'll spare you. If we set x perp to be x minus this formula, we see that as desired, x perp dotted with y is 0. I won't write it out, but I'll talk you through it. If you dot this with y, what happens? You get x dot y, and then you dot this with y. So you have a y dot y with a scalar.
You have x dot y minus x dot y.
So you have x dot y here, the y dot y cancels the denominator, and I have x dot y minus x dot y is 0. So it worked. Okay. So this vector here is so important, we're going to give it a name. We're going to call it the projection of x on y. This is telling us if you take a vector x, the part of it that goes in the y direction is given by that formula. If you've done some physics, you know that this is a convenient thing to do. If you've ever done computations with torques and such things, you actually want to think a lot about projections of the vectors onto other vectors. Okay, so let's do an example, and then I want to talk about this a little bit more. So if I take x to be the vector 1, 2, negative 1, 1, notice I'm out of the plane now, and y is the vector 1, 1, 1, 1, what's the projection of x on y? So,
Plug and chug.
so this is plug and chug. This is not very exciting, but I.
Can't you determine that it's going to be?
So I have to do this formula. I'm going to talk in a minute about how you should remember this formula. X dot y. What's x dot y? 3, right? 1 plus 2 minus 1 plus 1. Add it up. So it's 3. What's the magnitude of y squared?
1.
And then times the vector y. Done. Now, okay, big deal. So what does this tell me? Well, I want to make one comment, and then I'm going to get back to the geometry question. If I took this vector for y and asked you what the projection is, you get that answer. What would you get if I asked you for the projection of x on 6y?
Scalar?
You just have a 1 and 6 vector in the front as well.
Well, let's think about that. I pick up a 6 here, and a 6 here,
Right.
and what down here?
30. Yeah.
So what happens?
6 to 4.
It comes out the same. Tell me why that was obvious in the first place.
Because projecting it, like, you're basically projecting it onto the line.
Yeah.
So you're not actually like changing the shape of x rather than, it's the same line because it's parallel.
It's the same line, whether you use this vector for y or this vector for y, you're still going to get this same vector for x parallel. That's how you can remember this formula. So the important observation here is that if you do cy, let's do a different letter, lambda y, and then your magnitude of lambda y squared times lambda y, this is the same. The lambdas all cancel. We just said that. Here's how you can understand that. Think of a unit vector in the direction of y. Pull one of the magnitudes of y so that it's divided into y. And then you're left with what in front of that? You're left with x dot, the unit vector in the direction of y. Right? I have a net magnitude of y squared in the denominator, x dot y in the numerator, multiplying vector y. But if I regroup and put the magnitude of y under the vector y, I'm dotting x with the unit vector, multiplying by the unit vector. So that obviously is not going to depend on anything but the direction of the vector y.
I just mean like unit vector, like it's been noted like with y and like a little like triangle
Y
thing
hat.
above it.
Physics books like to use a little hat.
Oh, okay.
What do math books use?
They don't.
What is that?
Yeah. So how should you remember this formula? We're going to be using this formula all semester and it will come up again next semester. How are you going to remember it? It has to be a multiple of y because I'm projecting onto y. I'm finding the part of x along the y direction. So it has to be a multiple of y. You have to remember that the dot product comes in there. Okay, the dot product's there. And then this factor is just normalizing it exactly so that this happens. So that if you stretched y, you get the same answer. So because y appears quadratically upstairs, it has to appear quadratically downstairs. And that's how you remember the formula. Or you think of it. Okay, end of the geometry now. Well, all right, I'll draw it again. So how do I use this to actually give the angle? Well, I got myself a right triangle there. I just put it on the wrong board, but this right triangle's there. I've got my blue vector y here. I've got my orange vector x parallel. And I've got x. And I've got myself a right triangle here. So, gee, for good measure, put in a theta. And what do I have? Well, I know x parallel, and I know x. So what trig function relates those? Cosine. Now, I'm going to cheat here and leave a little extra room. So do that when you're taking notes. But would you agree that the cosine is the length of x parallel over the length of x?
Yeah.
Okay. So let's figure out what that is. Okay, so what's the length of x parallel? There's x parallel. Well, what's the length of this vector?
The part on the left, because the other one is a unit vector.
This is a unit vector, right? So the scalar in front is going to give you the length. And then I divide by length of x. And so here's this beautiful symmetric formula. The dot product of x and y divided by the product of the lengths. Beautiful formula. Which, as I said 30 minutes ago, is often taken as the definition in many books, including physics books, right? If you clear denominators, you get this formula. Okay. So now you know how to figure out cosine theta. So what's wrong? Why did I leave space? Something's fishy.
You have to make sure it's the sign length of.
This number could be negative. I didn't do an example yet where it's negative, but it certainly could be negative. Cosine theta could be negative. What's the picture that you have when cosine theta is negative?
Goes down.
Not fourth.
Second and third.
If your triangle looked like this,
Second or third.
what's the cosine going to be?
Greater than 90 degrees.
No, the angle is greater than 90 degrees. The cosine is
Gonna be negative.
negative.
It's the-
And in fact, in this picture, when you draw your reference triangle here, this is the length that you're doing when you do the cosine of theta, but it's with a negative. So the correct thing to put here is sine length, and that length is positive when cosine theta is positive, and that sine length is negative when cosine theta is negative, and that's exactly happening when x is pointing opposite to y. Generically, I don't mean literally opposite, but in the opposite direction to y. Okay. So this formula looks really cool, so I could go back to my example. What's the angle between x and y? So with that x and that y, what's the angle between them? Well, what's the cosine of the angle?
Dot products over.
The dot product, which we said was 3, over the product of the magnitudes. Well, we got the magnitude of y. Be careful.
Square root of 2.
Square root of 4, which is otherwise called 2. What's the length of x?
Or 7.
And so, what is the angle?
Cosine.
Our cosine. And by the way, WebWork will accept, if you just type in cosine to the -1 or our cosine, it will accept that, as long as you put parentheses about what you want. You can type in square root of 7, SQRT parentheses 7. And that's the answer. Okay. Question to ponder for Friday, and I'll pick up with this and do some more geometry with it. All these pictures were based on my drawing you stuff in the plane. How do you know that when you're in 27-dimensional space, or in fact, you're going to see examples later this semester and next semester where we're in infinite dimensional? So, especially those of you interested in physics and chemistry will care about this. Applications of this kind of stuff to infinite dimensional spaces. How do I know that it makes sense, if I'm in infinite dimensions, to say, define the angle by this expression? So in other words, I based all this on two-dimensional pictures. The question I'm going to pose here is, can we show algebraically, using just the algebraic properties, that this definition makes sense? In other words, I want to know that this is a candidate to be a cosine of an angle. What is necessary for that to be the case?
It has to be between -1 and 1.
Right. So I want to know that if I take the absolute value of that quantity, that it's less than or equal to 1. So on Friday, we will start with a proof of what's called the Cauchy-Schwarz inequality, and you will be using it multitudinous times throughout this course, which says for any vectors x and y in Rn, and in fact in greater generality than that, but don't worry yet, it is the case that the absolute value of the dot product is at most the product of the lengths of the two vectors. So we will prove this just by calculus and the algebraic definition, algebraic properties. And then you can say, so in any setting I want, this makes sense to find the angle. So we'll do that on Friday and then do some more geometry stuff and proceed from there.